Thank you very much for the introduction. Can you hear me well? Okay. Yeah, thanks for inviting me to speak here. So I will say a few things about some recent joint work with Francesca Janke. It's available on the archive. And I will start with some very general motivation. So earlier this morning, Udi mentioned the function field analogy, the analogy between the rational numbers and function fields of curves. So now I'm not looking at all of the primes, I'm just looking at a single prime. So this is sometimes called the local function field analogy. It's the analogy between the p-adic numbers and Lorentz series fields over Fp. But actually I want to discuss, so this is an analogy, but I want to discuss two methods which make this analogy very precise. So the first method is very familiar to people here. It's the method of sending p to infinity. And in case you're not a model theorist, or in case you're not familiar with this, so basically the idea is that as p goes to infinity, qp and fpt become more and more similar. So more precisely, you fix a sentence, let's say in the language of rings. Then for all sufficiently large primes, phi will hold in qp if and only if it holds in fpt. So that's a really remarkable statement. And of course, you can plug in for phi whatever you like. You can plug in some arithmetic statement which is of some interest. And okay, as the story goes, this is what happened. So Artin had conjectured that qp is a C2 field. So just to remind you, a field is called C2 if whenever you have a degree D hypersurface in d squared dimensional projective space, then you have a rational point. So Artin conjectured that this is the case for qp, but we learned that the truth is a bit more complicated. So Terjenan provided, so this is not quite true. Terjenan provided counterexamples in 1966 for p equals 2 and for general p in the 80s. But by using this asymptotic transfer principle, what Aix-Marseille showed is that they showed an asymptotic version of that, but it's important what the word asymptotic means here. It certainly does not mean that qp is asymptotically C2, that's simply false. What it means is that if you fix the degree of the hypersurface, then for all sufficiently large primes, qp will admit rational points in hypersurfaces of that type. Yeah, I should say that what they used actually is that essentially by a theorem of Lang, it was known that fpt is a C2 field. And although C2 is not captured by a single sentence, it's an elementary class, of course, but it's not captured by a single sentence. If you fix the degree, then it becomes a single sentence. Yeah, so here I stated this for sentences, but actually it goes much further than that. So you can consider formulas or you can consider integrals of definable functions, and there is a similar story in that setting. So here I'm referring very briefly to work of Hennenfent and Klager and many other people that have contributed to this subject. So this is one way to compare qp and fpt. But actually I'm going to look at a different method. So now this is a different game. Now p is fixed, but now the ramification, so here E stands for the ramification. The ramification tends to infinity. So I will explain later that this has gained some attention over the recent years, but actually some of the key ideas go back to this old paper by Krasner in the 60s. So as far as I know, he was the first person to realize that whenever you take a highly ramified p-adic field, it closely resembles a local field of positive characteristics. And that's a really key idea for everything I'm going to say, basically. And it was later understood that this works especially well by considering higher and higher wildly ramified extensions and by actually passing to the limit. So just to be concrete, let's say we take QP with, and now I join a compatible system of p power roots of p. And I also consider the corresponding object in characteristic P. So now you adjoin all these p power roots of t. And once you adjoin all these p power roots, you have the, this theorem by Fontaine-Wintenberger, again building on earlier ideas of Krasner. So the Galois groups of those, the absolute Galois groups of those two fields are isomorphic. And this was later generalized within the framework of perfectoid fields. So whenever you have a perfectoid field, you can define the tilt, which is a positive characteristic incarnation of K, so to speak. And the examples that I gave before are actually not quite perfectoid fields, so you have to complete them. So just to be consistent with, sorry? Okay. Okay, so in case you're not familiar with perfectoid fields, it's actually safe to think about just this example. Everything I'm going to say will have non-trivial content already for this example. But it's much more general. And the slogan is that K and K flat are very similar fields. They are very similar with each other. So for instance, you have a generalized Fontaine-Wintenberger theorem in this setting. And I should say that Solze also obtains a geometric generalization of this arithmetic statement for certain geometric objects which he calls perfectoid spaces. And in some sense, this theorem of Fontaine-Wintenberger, or the generalized version, is just a glimpse in dimension 0. It's just about points. So the motivating question, so 5 years ago, I think there was a meeting here, and there is this, there was a nice talk by Matthew Morrow that I watched on YouTube, but maybe most of you were present, actually. So what Matthew Morrow was basically trying to do, I think, was to prompt model theorists to look at the model theoretic, was to prompt model theorists to look at this tilting correspondence and try to understand it. So this is more or less what he suggested in the talk. I want to be slightly more precise, but again, I'm going to be intentionally vague. Okay. So a bit more precise is something a bit more precise that you can say is that is this question. So to what extent does the theory of K flat determine the theory of K? That's one thing that you can ask, and there's a good reason why I'm talking about this direction and not the other direction. I think it will become clear later. And also a closely related question is, okay, so K and K flat have different characteristics. One is of characteristic 0, the other one is of characteristic P, but you can still ask what kind of sentences can you transfer from K to K flat and vice versa. So you can imagine that lots of sentences would be transferable, given the similarities of those two fields. Okay, so these again are quite open-ended questions, but now I'm going to give some precise answers. So the first very formative observation, it's still unpublished, was made by Rideau, Scanlon, and Simon. So they observed that K and K flat are bi-interpretable in a certain logical framework. But the way I stated the result hides an important fact, namely that the interpretation of K and K flat requires parameters for the for the Witt vector coordinates of some element there. And this may seem like an unimportant detail or something, but it's actually related to an important phenomenon in perfectoid algebra, namely the phenomenon that if you want to go back from characteristic P to characteristic 0, there's not a unique way to do it. So in fact, here I just mentioned this example, but you can also take another example which also tilts to the same thing. So you can adjoin, let's say, P power roots of unity, and you will tilt again to the same thing.
So what do you mean by bi-interpretable exactly? It's not the usual notion that's still used, right?
Yeah.
It is?
Yeah, I think it's the usual notion.
Each one interprets the other,
and the composition is, yeah.
Okay, but you're saying it for K on the one hand and K flat join the constant on the other hand.
Yes, that's why I'm mentioning the parameters. Yeah, okay, yeah. That's why I included this exclamation mark.
Is this parameter definable on the other side or not?
You mean xi, the Witt vector coordinates of xi? No, it could be, for instance. What? I cannot quite hear what you're saying because you're very far away. Okay, yeah, sorry. I couldn't quite hear what you said. Yeah, so there are many ways to go back, and all these ways to go back are parameterized by an important object which is called the Farks-Fontaine curve. And this is the additional piece of information that you need. So you need this. Sorry?
Apparently we need lights.
Oh, we need lights.
It's éclair tableau.
Ah, okay. This one? Yeah. Is it better? Ah, okay. Maybe it's not better, actually. It's okay? Okay. Okay. So there are many ways to go back, and okay, so there's a moduli space which parameterizes all these untilts. And this is sort of the parameter that you need in order to know which point on the curve you're choosing. So something that I did in my thesis was to show that K is in practice decidable relative to K flat. So again, the subtlety has to do with the parameter, so you cannot always lift decidability, but as long as you can print one by one the Witt vector coordinates of xi, then you have such a transfer. The third answer that I'm going to discuss today is that if you pass an elementary extension of K, then you will find a well-behaved valuation in a certain precise sense that I will tell you in a few minutes, whose residue field is an elementary extension of K flat. So this is joint work with Francesca Young, and it's what I'm going to talk about. Okay. Oh, sorry. Again, this is the description, the informal description that I gave before. So here's the actual statement. So we start with the perfectoid field, and now I'm going to also introduce a non-principal ultrafilter, and I'm going to consider the corresponding ultrapower. Okay, so the perfectoid field, by definition, is of rank 1, But once I pass to the ultra power, I have introduced many convex subgroups. So now I can consider coarsenings. And here I'm taking the coarsest coarsening such that this pseudo-uniformizer has still positive valuation. So if you just want to look at the picture, so here's your value group in the ultra power. This is the value of var pi. And now you have some infinitesimal elements that you've created. So by infinitesimals, I mean, so the absolute value is smaller than, okay, maybe I should not use absolute value in this context. Okay, so smaller than any rational multiple of the value of var pi. And I just collapse this convex subgroup to 0. So now this is my new valuation. And the reason you want to do this is because after doing this, the valuation becomes really nice. So perfectoid fields can admit, for instance, immediate extensions. But, and these are, of course, well known to be an obstacle into understanding the model theory of a valid field. But once you pass to this coarsening, every finite extension is unramified. In particular, you have no immediate extensions. Everything comes from the residue field. So this is one part. It says that the valuation is nice. The second part, okay, but if you make the valuation nice, this does not come for free. So the residue field now is more complicated than before. But part 2 says exactly how complicated it is, and it's going to be the tilt in disguise. So it's maybe useful to draw a picture. So we have K, we have K flat, and there's this mysterious operation called the tilt. But after passing to this ultra power, this mysterious operation becomes a place. So in some sense, what people in perfectoid algebra have been studying, namely transferring, so studying K flat in order to understand K, is actually much more familiar to an idea. It's actually very similar, or closely, very much related to a phenomenon that is familiar to model theories. So we want to understand the valued field in terms of the residue field and the value group. But in this case, the value group is divisible. So most of the difficulties come from the residue field. Okay. The same problem as before. So maybe I should just use this. Okay. There's also a moreover part, which I'm not going to discuss much. But by part 1, you have an isomorphism of Galois groups. So every finite extension is unramified, so you get an isomorphism of Galois groups. And this restricts to the Fontaine-Wintenberger theorem. So the moral is that we have eliminated all difficulties related to the defect at the expense of making the residue field more complicated. But we know exactly how complicated it is. So now let me try to explain how one can use this picture without the moreover part to read off some information, well, to transfer information between K and K flat. So just by looking at this picture, one can say that the Galois group of K is elementary equivalent as a profinite group to the Galois group of the ultra power, because they have the same theory. This one is isomorphic to the Galois group of Kw because every finite extension is unramified. And Kw is an elementary extension of the tilde, so this also gives the last equivalence. So one gets just by looking at this picture, one gets a weak version of Fontaine-Wintenberger. Oh, sorry. Okay. Yes, regarding the property, now I'm looking at the property of being defectless, or Henselian defectless if you prefer. And let me just draw some additional piece of data that I forgot. So V bar is going to be the induced valuation of the ultra power of the non-standard valuation of Ku on the ResD field. And this is just V flat, which is incidentally, okay, so the ResD field is the same as the ResD field of K. Okay, maybe I can just remove this. So now by looking at this picture, so Kv is defectless, so this is this place. If and only if this is defectless, that's completely formal. But now I know that this is defectless by part 1. I know actually much more than that. So this is defectless if and only if, let me give this a name, so this is Vu. So this is defectless if and only if this is defectless. But this is an elementary extension of V flat. So this is if and only if K flat, V flat is defectless. So one can transfer the property of being defectlessness from K to K flat and vice versa.
But isn't K a perfectoid field?
Yes, but perfectoid fields can admit defect extensions.
But yeah, but can they ever be? They always have defects, right? Like
Well, of course, you can take a tame field of rank 1 and yeah, or algebraically closed. CP is a perfectoid field, for instance.
Okay.
Okay.
No, but I see. Okay.
Okay. So 1 and 2 are well known, but now I'm going to discuss. Okay, so I think people have not looked at the property of being CI. They have looked at it in general, but I'm in this context. So K is CI. Yeah, so the class of CI fields is an elementary class. So again, the first equivalence is formal. And the equivalence in the middle is simply because the ResD field of a CI valued field is CI. That's an exercise. And again, the last equivalence is formal. Okay, so this shows that if K is CI, then K flat is CI, but I think the converse is an interesting problem. So suppose K flat is CI is the same true for K. And there's not much evidence that this should be the case, apart from some sporadic examples maybe. Namely, the examples of Teryanan actually have rational points over perfectoid field extensions. I think the strongest piece of evidence is, okay, so I think the case I equals 1, there's a high chance that the case I equals 1 works. Okay. So there is some related work in this direction, but actually it's a bit more convenient to look not just at hypersurfaces, but at a more flexible class, a birational class of varieties, which is known to behave well with respect to specialization and so on. And then what one wants to prove is the transfer of existence of rational points in such varieties. So this is very much work in progress, I should say. So for the rest of the talk, I will just try to explain this picture. Okay, so here's part one again. So part one is just to remind you, this part which says that valuation is nice, and that's what it means to be nice in this case. So every finite extension comes from the residue field. Okay, so I will try to explain in the next few minutes, okay, that this is essentially a non-standard version of the almost purity theorem, and more precisely over perfectoid valuation rings. So there are many versions. And this version is usually attributed to Tate and Gaber-Amero. And if you just look at the statement, you will see that it's actually very similar. So now you do not take any ultra powers or any coarsenings, but the conclusion is that every finite extension is almost unramified. So I have to explain what this almost means and why it's related to the previous version. But actually, this terminology is not used. So it just so in almost mathematics, we do not people do not say that a finite extension of value fields is almost unramified. Usually, this is captured by saying that the extension of valuation rings is almost finite et al. So I will explain these terms, mostly with examples. Before I do that, okay. There are more general versions of almost purity. So namely over perfectoid K algebras, and this was first done by Faltings under a technical assumption. It was proved in full generality by Solze, and then recently André gave a version where he also allows some ramification to occur over the generic fiber. Okay. So now, so the goals for the next 15 minutes or so will be to explain the key ideas in almost mathematics, explain why part one is a non-standard version of almost purity. More generally, I want to make precise the connection between the two frameworks. But yeah, this was really a small glimpse. Yeah, so this will just be a small clip. So this is a technical subject, but it's technical, but I think the key ideas are surprisingly simple, and I don't want to focus on the technical details that much. I just want to illustrate what the key ideas are and why actually it's a very familiar game if you phrase it in the correct language or in some language. Okay, but first I'm presenting the usual version. So I will try to explain the notion of an almost et al. Extension. Okay, so I will give you an example. Okay, so I take K to be the usual field, and for this example, let's say that P is not 2. So now I'm just adjoining, consider a quadratic extension, I join square root of P. So classically, this is a totally ramified extension, but I will argue that in some sense it's very close to being unramified. So said differently, the extension of valuation rings is very close to being et al. So let me just look at what happens at the finite level. So at the finite level, I just consider this finite approximation, so to speak. So now I just adjoin a p to the nth root of p for a fixed n. and Kn prime is the corresponding quadratic extension. Okay? So it's an easy exercise. Now that you have local fields, the extension of evaluation rings is finite. There are no complications with that. And it's easy to describe. You just take a square root of a uniformizer. And in this case, you take a square root of p to the 1 over p to the n. Okay, let me go back maybe. Oh, not that back. Okay, Kn prime. Yeah. And so in what sense is this extension of evaluation rings close to being a tuple? One way to look at it, it's not the only way, is to look at the modulo of Kähler differentials. So this modulo of Kähler differentials is not 0, but what happens is that it's killed by an element of very small valuation. So here, p to the 1 over p to the n has valuation 1 over p to the n, and as n becomes large, this has smaller and smaller valuation. So it's not 0, but it's close to being 0. So then you can pass to direct limits and get that the modulo of Kähler differentials of the original extension of evaluation rings is killed by all these p power roots of p. So it's killed by all these elements of very, very small valuation. And in almost mathematics, you want to ignore almost 0. So this is an example of an almost, what we will call in a few seconds, an almost 0 module. And we want to ignore, we want to build a version of ring theory where such modules are ignored systematically. So that's the idea. And now let me explain how one can do this. So this is the basic setup for formalizing this idea. So we start with a perfectoid field. OK is the valuation ring, M is the maximal ideal. And first we start with OK modules. Algebras will come later. And the way you usually ignore things, or sometimes a very efficient way of ignoring something in mathematics is to pass to a quotient. So if you have an abelian category and you have what's called the Serre subcategory, so this requires to be closed. It's a full subcategory which is closed under extensions. Then you can form the quotient. And this quotient in this case is called the category of almost modules. So, so if you run this construction for QP for something which is discrete, actually this would already stop here. I mean, this would not be the category of M torsion modules would not be a Serre subcategory. It's really crucial that M squared equals M, so to speak, in order to form the quotient. So this is just a piece of notation. I will use this notation for the almostification functor. So the functor which takes M to its canonical image in the quotient. And you may complain that I haven't given a formal definition of this, but I will try to give an intuition now. So I will try to justify why one can think of this almost module M as a slightly generic fiber of M. So let me draw a picture. So this is the category of, just the usual category of OK modules. And then we can take a module, an OK module, and we can take its generic fiber. So the category of almost modules sits somewhere in between. And the reason I have this factorization is because if I have an almost 0 module, so if it's killed by the maximal ideal, then definitely the generic fiber is 0. So in some sense, this functor descends to the quotient, so to speak. And this is the canonical almostification factor. But actually something interesting is happening. So this explains why, this sort of explains by a diagram why this is somewhere in between. But actually this is a very strange picture because OK is a valuation ring of rank 1. So in fact, there is no actual notion of a slightly generic fiber. Whatever you invert in OK, no matter how small the valuation is, it's going to give you everything. It's going to give you the whole of K. But somehow one is able to make sense of the category of modules over a slightly localized ring, which does not quite exist. So it's a very peculiar situation, but it will make sense. Maybe this already hints at what's going to happen. Yeah, so this is not quite true. We do not have a notion of a slightly generic fiber in the algebraic sense. So this, so this category is not quite the category of modules over something, but it behaves like one. So it's a tensor abelian category, and whenever you have such a category, you can define many notions categorically. So for instance, you can define the notion of an algebra. You can define flatness. It's going to be categorical flatness. But there are some subtleties. So, so for instance, the notion of categorical projectivity is going to give you the wrong notion. So you need to borrow back some ideas from commutative algebra. And eventually, one defines the notion of an étale extension in this context. Okay, so now I'm starting over again. And I'm looking at the same. Okay, so I'm looking at the same example as before, but now. Okay, so just to remind. Okay, this was the setting, but now I'm going to look at the situation at the ultra-power level. So I consider the ultra-powers, I make the coarsenings, and now I'm in this localized situation in the coarsenings. And of course, once you do that, okay, this is a much more familiar game. Once you do that, nice things will happen. So K prime, so the first step is to write K prime not by adjoining. You can represent K prime as K, where you adjoin not the square root of P, but the square root of P to the 1 over P to the n. And this is true for every n. So now I can take the limit, which wasn't available before, and I can express my extension in this form. And if you present your extension in this form, it's very clear what happens. Now the extension of valuation rings is finite. It's not anymore almost finite or anything like this. And it's going to be an honest finite étale extension, since P is not 2. Wait, what? Okay, so this, so the almost étale extension that we saw in the previous example transformed into an honest one. So this hints at a dictionary between the two frameworks, which I will try to explain next. So this fits into a much more general framework. Okay, so this slide is, okay. This slide is a bit technical, so I will not read everything that's written here. But basically, this dictionary is explained via a functor from the category of almost modules to the category of honest modules over OW, which takes an almost module and it sends it to the localized ultra-power. And this functor is such that it translates, okay, under a technical assumption, which I'm not going to discuss, it translates almost ring theory into usual ring theory in the expected way. I recently became aware of this construction due to Gaber, which is has a very similar flavor, but he's not quite considering an ultra power. He's considering something quite close, actually. And it was used to simplify a proof and to simplify a step in the proof of the direct summand conjecture. So he used this actually to pass from. Okay, it doesn't matter. But what I will say is that there will be a discussion. So in the first version of the paper, there's no discussion or comparison between those two frameworks. But in the next version, there will be a paragraph or something like this explaining the similarities between those two approaches. Okay, even from the notation, it looks very, very similar. Wait. Oh, it's frozen now? Ah, okay. Yeah, so this was part one. So part two was the part. So part two is the part which says that the residue field is the tilt in disguise. So here's the usual setting. You take your perfectoid field, you pass to the ultra power, you make the coarsening, then K flat, V flat embeds into KW, even elementarily. I mean, that's the emphasis actually of this part. So I don't think I will be able to describe I mean, it's not really interesting. Well, it requires a bit of algebra. I mean, I don't want to present it right now. What I will say is that it's actually very natural, and it's also quite easy to check that once you have this embedding, it induces an elementary embedding at the level of truncated valuation rings. So if you look at this map, which I haven't introduced, and you look at the induced map iota bar at the truncated level, then this will almost be a diagonal embedding into an ultra power once you unwind the definitions.
So what is T?
So T, okay, you just choose a pseudo-uniformizer in K. I mean, let's use this example. So T is going to be literally P to the 1 over P, P to the 1 over P squared, which lives in K flat, which you can think of as the inverse limit of. So you can take this as T. So it's a diagonal embedding modulo some Frobenius twist that's happening. So the interesting thing is how to go from this, how to use this to actually show that the map iota is elementary. So one would need to know an Aix-Marseille principle for certain valued fields down to truncated valuation rings. But the question is, what are the valued fields? For what kind of valued fields? So here we need to be a bit flexible. So KW is not quite a perfectoid field. So we need to work with a larger class of valued fields that includes perfectoid fields. But this better be also an elementary class. So I will present this class. So fix a prime P. C is going to be the class of valued fields together with distinguished element in the maximal ideal, non-zero, such that KV is Henselian of residue characteristic P. O mod P is semi-perfect, so the Frobenius is surjective. And this is really crucial, and I will get back to it in a few seconds. So we ask that the valuation ring, after inverting var pi, it becomes algebraically maximal. So I will view structures in this class as L-val var pi, so as structures in the language of valued fields with a constant for this element var pi. So first, an easy fact, perfectoid fields are in C, so everything is clear. Third condition, just note that whatever you invert, you get everything, you get the trivial valuation. What's not so, actually that's a very delicate point. So C is actually an elementary class, and this is not at all obvious. Because if you look at axiom 3, it's not at all elementary by itself, even in conjunction with 1. So this is tricky. Now, valued fields in C can be understood modulo O mod var pi. And the reason is that such a valued field can be tamed in a precise sense that I will explain in the next slide, so that the residue field is controlled by O mod var pi.
Sorry, QP belongs to the class C, or?
Here I'm considering also, yes, this includes also unramified mixed characteristic fields. Of course, the case of interest is when the value of P is not minimal positive. But for the X cosines of...
You don't require it, so you allow QP for that.
Yeah. Yes, but actually the case I have in mind, what I will say next holds for QP, but it doesn't give you anything new, or also in the unramified case. So it's a bit better to think that VP is not minimal positive, but I'm not requiring it. So it's not a type. Yeah, I know. Yeah, but this is not a typo. What I will say also holds for this. So take an extension of such fields. I have just included the conditions to remind you. Then the following are equivalent. K is an elementary substructure of K prime, if and only if the extension of truncated valuation rings is elementary and the extension of value groups is also elementary. Yes, in the case of unramified mixed characteristic Henselian fields, this would be a classical statement, for instance. Then for var pi equals P, let's say, this would be just the usual story. O mod var pi would be the residue field. But actually, if gamma and gamma prime are regularly dense, then the value group condition in 2 can be omitted. Okay, and the key ingredient to proving this theorem is the model theory of tame fields, which was introduced and studied by Franz Victor Kuhlmann. And this is really the key that unlocks the model theoretic results contained in this paper. This, in combination with the fact that the valued fields I'm considering can be tamed, can become tame after passing to the ultra power and making a coarsening. So this applies to the previous situation. So we had this embedding which induced an elementary embedding of truncated valuation rings. So and the value groups are regularly dense. So this applies to show that this is elementary, but it also has some other applications. How much time do I have?
10 minutes.
10 minutes, okay. So yeah, I wasn't expecting this, but actually I will be able to discuss about other applications. Okay. Are there any questions so far? Actually, maybe I was going fast, I don't know. Okay, because now I'm going to move to something, it's not totally different, but yeah.
What is the relation between the Scanlon with the also product of Florence Sylvain and the between these things you're taking off the product, dividing by the courses.
I'm not entirely sure. I mean, I'm not very. Maybe Tom can say something about this or not. Okay. I'm not sure. Okay, so now something different. But actually it's not that different. Okay, so yeah, so we had this Aix-Marseille principle from before, and this was applied for this part. But you can do also other things with it. So this is a classical problem. So is the Henselization of FPT an elementary substructure of the power series, of the power series field? And of course, the theory of FPT remains elusive. But what you can do is prove the following. So you can just prove the perfected version of it. So the perfect hull of the Henselization is an elementary substructure of the perfect hull of FP double brackets T. And the reason you can prove this is because you can just look at the quotients modulo T and see that they're equal. But unfortunately, this does not seem to shed any light on the theory of the perfect hull of FPT itself, because then you have just moved all of the difficulties to this highly complicated. I will just write it. You have removed all of the difficulties to this highly nilpotent FP algebra. It's not at all clear if it's an improvement, but at least you get access to statements like this. So this is one application. Okay, there are many other applications of similar flavor contained in the paper, using the same trick, basically. Another application is that tilting respects elementary equivalence, but one needs to be very careful. So you have to fix a base. So let K1 and K2 be two perfectoid fields, extending a base perfectoid field K. Then K1 is elementary equivalent to K2 over K if and only if K1 flat is elementary equivalent to K flat, to K2 flat over K flat. Oh, sorry. So if you set K equals K1, this means that tilting respects elementary substructure. So K1 is an elementary substructure of K2, if and only if K1 flat is an elementary substructure of K2, K2 flat. But without fixing a base, the reverse direction is not true in general. So I forgot to complete again, although yeah, probably I sent the wrong version. Okay, so here I should have completed those two fields, but the point is that they give rise to the same perfectoid field in characteristic P, so you cannot go back if you do not fix a base.
Like here, the example is still
like the example here, yeah. So these two fields are clearly not elementary equivalent. There's another way to go back, which is more in the flavor of the Witt vector story that I explained before. So in that story, you have to fix the type of the Witt vector, or more precisely, the type of the sequence of coordinates of the Witt vector, and then you can also go back. But I think this. Okay, I'll just stop here. Okay, okay. That's it.
Thank you very much.
More questions.
So, have you concrete examples of elementary equivalent perpetuate fields besides the case of the 2 times the same field or 2 algebraically closed perpetuate fields?
Elementary equivalent perpetuate fields. Okay.
Yes.
I mean, you can take, for instance, tame fields of characteristic P, and then you have the Kuhlmann technology. So, for instance, you could take let me think. Yeah, so for instance, taking 2 tame fields of rank 1 in characteristic P with the same value group, or with let's say with the same value group and same residue field, but which are not identical. Then Kuhlmann gives you that they are elementary equivalent. In mixed characteristic, I have to think about it. I don't have an example off the top of my head. Okay, I have to think about it. Okay. I mean, you can always untilt. I mean, that's a cheat, of course, but you can always untilt to yeah, okay, but it's a bit trivial.
Just a quick remark. If recent work of mine with Dale Katkowski is correct, then, and the paper is almost finished, then the Kähler differentials that you showed us in your little example are not only almost 0, they are 0.
I think it becomes 0 if you take the module Kähler differentials of the algebraic over the algebraic closure, but even for finite extension.
Exactly for that example that you have,
okay.
Yes. The reason is actually that the value group is P divisible. And that is used to show the computation is not the same computation as you indicated there. It's a direct computation that is also done for more generally for deeply ramified fields. And in the case of deeply ramified fields, you can even look at wild ramification so in mixed characteristic. And even there, the omega is 0. And again, it's a matter of the value group or Archimedean components of the value group not being discrete.
Okay, thanks.
Do you recover proof that finite extensions of perfectoid fields are perfectoid?
Yes, you can prove this using some results, some quite more elementary results about tame fields. Yeah, so you can show that the finite extension of tame field is. Okay, I will not give you the proof right now, but it's actually contained in the paper. So we prove almost purity, the part of almost purity which says that the extension of evaluation rings is almost a tuple, but we also include the finite ascent statement, and this uses just some basic facts about tame fields again. Yeah, so this is included in the paper.
More questions?
What's the definition of perfectoid field?
Yeah, thank you. Okay, what's the that's a good question.
That's the empty board over there.
Okay. So a perfectoid field is a valid field, first of all, and it's of residue characteristic P greater than 0. And the first condition is that it's complete.
So V is a real valuation.
I haven't finished the definition yet. Okay. So now the value group, yeah, it's a real valuation. Okay. It's a real valuation and it's non-discrete. And the third crucial condition, which we saw before, is that, okay, so you have to, you want to have some meaningful notion of being perfect in characteristic 0, but of course you're always perfect. But you want to capture the idea that you can extract lots of p-power roots of elements, like the examples over there. So you have a meaningful Frobenius now in O mod P, which is a huge ring, and you ask that this be a surjective map. So that's the definition.
Any further questions? Everybody happy? Then let's thank